So we're in section 9.3. And we're going to talk about geometric sequences. As soon as this thing starts working the way I need it to. So we'll start by talking about geometric sequences. So again, a sequence is just a list of numbers. We have a function where our function values, our domain of the function is the positive integers. So we're plugging in 1, 2, 3, 4 into our function, just like we did on this problem here on the board. We started at 0 for this one. So a geometric sequence is different than an arithmetic sequence. Arithmetic sequence, we added a number to each previous term to get the next term. For a geometric series, we multiply a term by a certain number to get the next term. So we're just going to multiply a term by a fixed number to get the next term. And the way we write that is that a sub n, our nth term, is the previous term, a sub n minus 1, times r. And we call r the common ratio. So with an arithmetic sequence, we had a common difference. D was our common difference, the number that we added to each term to get the next term. For a geometric sequence, we have a common ratio. We multiply by this number to get a common ratio. And we can find the common ratio if we have a geometric sequence. We can find the common ratio just by dividing one term by the previous term. So let's look at a couple of examples of that. If we have a geometric sequence, and we want to find the common ratio. So our first geometric sequence is 3, 6, 12, 24, ... How do we find the ratio? What's our common ratio here? Times 2. We multiply each term by 2. R equals 2. We could find that by 6 divided by 3 is 2. 12 divided by 6 is 2. We can divide any term by its previous term to get the common ratio. So our common ratio is just 2. We're multiplying by 2.
Question.
Yes?
So do you use D for subtraction and addition and then R for multiplication?
Yes, so the question was, do we use D for subtraction and addition? For arithmetic series, we use D, the common difference, and R we use for multiplication, and we call it the common ratio. Same idea. One is addition, one is multiplication. Let's look at another one. We have a sequence 1, 1/2, 1/4, 1/8. Our common ratio here, what's the common ratio? What is it? Divide by 2, or times 1/2. R equals 1/2. If we divide 1/2 divided by 1 is 1/2. 1/4 divided by 1/2 is 1/2. Any term divided by its previous term is 1/2. So we get the next term by multiplying by a half. So finding the common ratio, like finding the common difference, pretty easy, pretty straightforward. Any questions on that? Now, like we did for an arithmetic sequence and for our sequences that we did before, we want a formula for the nth term. We want to be able to plug in n equals 1, 2, 3, whatever, and figure out what the nth term is. So let's come up with our nth term formula. So if we know the ratio and we know the first term, or we know a term and we know the ratio, how do we find the nth term? That's big part of what we're interested in with our series. So we start with a sub 1, and we have our common ratio. Our common ratio equals r. So we start with a sub 1. A sub 2 is a sub 1 times r. We multiply our first term by the common ratio to get the second term. A sub 3 is a sub 2 times r, but a sub 2 is a sub 1 times r, so that's a sub 1 times r, or a sub 1 times r squared. A sub 4 is a sub 3 times r. But a sub 3 is a sub 1 times r squared. So this is a sub 1 r squared times r, or a sub 1 times r to the third. Let's do one more and see if we can figure out the pattern. A sub 5 is a sub 4 times r. And a sub 4 is a sub 1 times r cubed. And that's a sub 1 times r to the fourth. So if we keep going, our nth term, what is our nth term going to be? A sub 1 times r to the n minus 1. Perfect. So our nth term is the first term times r raised to the n minus 1 power. So that's how we find, that's our nth term formula. And this is going to be an important formula for geometric series, just like our nth term formula was important for arithmetic series. This is how we find our terms. Questions on our formula? All right, let's find a few nth terms. Let's look at a couple of examples. We have, we want the nth term. Nth term equals something. If a sub 1 is 5 and r is 2. So this one's easy. We just plug into our formula. A sub n is 5 times 2 to the n minus 1. That's our nth term. Questions on that one? So let's look at something a little more complicated. Let's find the 20th term. The 20th term of this sequence. 1, 3, 9, 27. And it keeps going. So what's our first term here? A sub 1 equals what? 1. What's our common ratio? What is it? 3. Common ratio is 3. So our 20th term, a sub 20. I plug into my nth term formula. A sub 20 is 1 times r to the 20 minus 1. R is 3, so 1 times 3 to the 19th. And if we multiply that out, we get 162, 261, 467. 1 times 3 to the 19th. So I raised 3 to the 19th power. R is 3. Our 20th term is... Right, so our first term is 1. Our ratio is 3. N minus 1 is 19. We're just plugging into this formula. So we can see that geometric series grow very quickly. If we multiply by 3, we get out to the 20th term, and we have this huge number. So geometric series grow extremely quickly.
Sorry, is that one number?
Yes. If you put 3 raised to the 19th power in your calculator, you should get that. Questions on that one? We're just plugging into our nth term formula. All right, let's look at a little more complicated example. We want the 15th term if a sub 3, the third term, is 5/4, and the sixth term is 5/32. A sub 6 equals 5/32. We want the 15th term. So when we have a problem like this, when we have two terms, we have two things that we need to find. We need to find r, and we need to find a sub 1. We need to find our first term to come up with our nth term formula. So I'm going to write the nth term formula for each of these terms. So we know that a sub 3 is 5/4, and that equals, thank you, C204. A sub 3 equals A1 times R to the n minus 1. N is 3. R to the 3 minus 1, R squared. So we know that A sub 3 is A1 times R squared. A sub 6 equals 5/32, and that equals A1 times R to the n minus 1. N is 6, so R to the 5th. I have two equations. Two variables. How do I solve two equations with two variables? Cedric? We could solve for the pattern. Is there another way that we learned in algebra? Solve for one variable, substitute. Okay, so let's do it that way. I think that's going to be a little easier. So a sub 1, I'm going to solve for a sub 1. I know that 5/4 equals a sub 1 times r squared. So a sub 1 equals 5/4 times 1 over r squared. I just divided both sides of this equation by r squared to get a sub 1 by itself. Divide both sides by r squared, I get 5/4 times 1 over r squared. Now I'm going to substitute a sub 1 in right here. So 5/32 equals a sub 1, which is 5/4 times 1 over r squared, times r to the fifth. Or r to the fifth divided by r squared is what? R to the third. So 5/32 5/32 equals 5/4 r to the third. If I multiply both sides of this equation by 4/5 to get rid of that fraction, I get r to the third equals 1/8. And r equals the cube root of 1/8 equals 1/2. So r equals 1/2. Now I can plug that into either one of these equations to find a1. I already solved this one for a1, so let's plug r into this equation and solve for a1. I'm going to plug this back in here. So a1 equals 5/4 times 1 over 1/2 squared. I can do it this way, 1 over 1/2 squared. I'm just plugging 1/2 into this equation. And when I simplify this, I get a1 equals 5. So now I have my common difference, and I have my first term, and I wanted my 15th term. So I know that a sub 15 equals a1, which is 5, times r, which is 1/2, to the 16th power, or the 14th power, sorry, r minus 1. So a sub 15 comes out to be 5 over 16,384. Where? Here? The problem told us that our sixth term was 5/32. And using our nth term formula, a sub 6 is a sub 1 times r to the fifth, r to the n minus 1. So that's where that r to the fifth came from. A sub 6 is a sub 1 times r to the fifth. And a sub 3 is a sub 1 times r squared. Okay? We solved this equation for a sub 1 by dividing both sides by r squared. So we had 5/4 equals a sub 1 times r squared. So a sub 1 is 5/4 times 1 over r squared. Then I substituted this into this equation to get my r. Okay? All right. Questions on that example? We did a similar one for arithmetic sequences. All right. So we want to find the nth term. We want to figure out what our nth term is from our common difference. The other thing that we're interested in sequences is the sum. So we want our formula for the sum. And for our first sum, we're looking at a finite geometric sequence. I'm not going to go through how we come up with a formula. It's not difficult. If you're interested, I can show it to you. It's not hard to come up with. But the sum of n terms and the other way we say this, the sum of n terms, or the nth partial sum, and we write S sub n. S sub n is a sub 1 times 1 minus r to the n over 1 minus r. and r for this does not equal 1. So this is our second important formula for geometric series. Just like arithmetic series, we had an nth term formula, and we had a partial sum formula. For geometric sequences, we have our nth term formula, and this is our sum of n terms, or nth partial sum. These two both mean the same thing. So for our sum, we need the first term, and we need to know the common difference. So those are the two things that we're always interested in with a geometric sequence. First term and common difference. If the problem doesn't give them to us, we need to do some more work to figure them out. So let's look at an example of calculating with this formula. Question, Jacob, or are you just stretching? Okay. So here's our example. We want to evaluate the sum n equals 1 to 20 of 2 times 0.01 to the n. So what this problem is asking us, it wants the sum of 20 terms So the sum of 20 terms, or the other way of asking this question is the 20th partial sum. Both of those questions mean the same thing. What is the sum of 20 terms, or what is the 20th partial sum? That's what this is asking us. So we need to know a sub 1. What is a sub 1 for this sequence? What's our first term? Yes, Cedric. What's that? Point what? 0.02. So we're substituting. Let's see. Did I write this? I didn't want 0.01. I want 0.1. 0.1 to the end. So you would have been right if it were 0.01. So what's our first term here? 0.2, right? I substitute n equals 1. So 0.1 to the first power is just 0.1. 0.1 times 2 is just 0.2. What's the common difference? What are we multiplying each term by to get the next term? 0.1. Our common difference is 0.1. So we multiply our first term by 0.1 to get the second term. We multiply the second term by 0.1 to get the third term. So this 0.1 is our common difference. So our sum, the 20th partial sum, or the sum of 20 terms, is 0.2. The first term times 1 minus our common difference, 0.1 to the 20th power, all over 1 minus 0.1. And if you plug that into your calculator and you calculate, you should get 2 ninths. And you can put it in your calculator, just like this. What's that? For our formula, our sum is this whole thing. We calculate that whole thing out. Okay. What's that? This is just our first term. Okay.
So why isn't 2 the common difference?
Well, if we wrote this out, our first term would be 0.2. Our second term would be 0.2 times 0.1 squared. So we're multiplying by each time by 0.1 to some. We're multiplying each time by 0.1. So we start with 0.2. Our second term would be 0.2 times 0.1. Our third term would be 0.2 times 0.1. That times 0.1. So each time we're multiplying by 0.1. Does that make sense?
Yeah.
All right. The last thing we need to talk about. Question, Josh? Okay. Last thing we need to talk about today for geometric series is the sum of an infinite geometric series. So the last formula we came up with was for the sum of a finite geometric series. One of the nice things about geometric series is if we have a common ratio that's nice, we can add up an infinite number of terms and come up with a number. So let's look at our formula. S sub n was a sub 1 times 1 minus r to the n over 1 minus r. If absolute value of r is less than 1, so that means our common difference is some kind of fraction, 1/2, 1/3, some kind of fraction. If our common ratio is less than 1, we have some kind of fraction. If we're raising a fraction to an exponent that gets bigger and bigger and bigger and bigger, what happens to the number that we get when we raise the fraction to a bigger and bigger and bigger exponent? It gets smaller. So if we have a fraction and we're raising it to these huge exponents, it gets smaller and smaller and smaller and smaller. Eventually, as n gets really, really, really big, this term, this 1 minus r to the n, if this is a fraction, this r to the n gets really, really, really tiny. And in fact, eventually it goes to 0. So our sum, if r is less than 1, as n gets very large, our sum just turns into a sub 1 times 1 minus r. This r to the n becomes 0. 1 minus 0 is just 1. So we're just multiplying the top by 1. So our sum of an infinite geometric series and we write as n approaches infinity. As n gets very large, the sum of an infinite geometric series is just a sub 1 times 1 minus r, and our condition is that our common difference has to be a fraction, some kind of fraction that's smaller than 1. It can be positive or negative, but if our common difference is a fraction, we can add up an infinite number of terms and come up with a number. And that's one nice thing about an infinite geometric series. So let's look at a quick example before the bell rings. So if we have a sum, n equals 1 to infinity, of 2 times 0.4 to the n minus 1. For this particular series, a sub 1, if I plug in n equals 1, n minus 1 is 0, 0.4 to the 0 is 1, and my first term is 2. So a sub 1 is 2. R is 0.4. So if we add up this infinite series, our sum is 2 over 1 minus 0.4, which equals 10/3. So if we add up an infinite number of these terms, we end up with 10/3. We end up with a finite number. All right, homework.
Yeah, I got my flash drive.
All right, there you go.